Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 3450, Mission to Mars, Lecture 7, the Apollo Program. In the last lecture, we talked about the early history of human spaceflight. In this program, we're going to talk about what many people consider to be the pinnacle of human achievement when it comes to spaceflight, and that's the Apollo program, the missions to the moon. Now, I'm going to assume that you have already read Andrew Chaikin's book, A Man on the Moon. I consider it to be the definitive history of the Apollo program, and I think it's a great place to start when you're studying Apollo. It gives some brief history of the Apollo program. It talks about each of the missions in detail. It talks about the biographies of the astronauts. I think it's just a fantastic book about the Apollo program. Because I'm assuming that you've already read this, therefore, I'm not going to go into detail as to what happened on each of the Apollo missions. You'll get that from the book. I will do a brief summary of what happened on each of the Apollo missions, and I will focus on the science, what they were hoping to accomplish, and what we learned from each of the Apollo missions. So Apollo program history begins in 1959 with NASA's Space Task Group. You'll remember from the last lecture that the Space Task Group was tasked with figuring out how to get an American into orbit around the Earth, that is, how to get a human into space. In 1959, they also began planning for a potential crewed lunar landing. And I believe this largely comes from the inspiration of Jules Verne's From the Earth to the Moon. Many people in the early space program were inspired by Jules Verne's work, and they figured that it was the natural progression of human spaceflight was to land humans on the moon. It was also prudent to believe that the Soviet Union was doing the same thing, and since the U.S. was in competition with the Soviet Union, in a space race and a Cold War at the time, it was natural for the United States to try and plan to do this. In 1960, the Space Task Group created Project Apollo as a follow-on to Project Mercury. You'll remember that Project Mercury could sustain a single astronaut in orbit for up to a day. Going to the moon was going to take substantially longer, possibly as long as 2 weeks. And so the Apollo program would need a capsule that was much more capable. It would need to hold 3 astronauts for a longer period of time. So they began planning for this much more ambitious Project Apollo. Eventually, they would realize that many of the skills that would be needed for the Apollo missions to succeed would require practicing with 2-man crews and longer missions, and so Project Gemini was inserted between Project Mercury and Project Apollo as a build-up, as a practice for Project Apollo. And then, of course, the United States was surprised on April the 12th, 1961, when the Soviet Union announced the launch of Yuri Gagarin and the fact that he had completed a single orbit of the Earth. And this was once again a devastating blow to the United States' prestige. They had lost the initial space race. The Soviet Union had beat them into launching the first artificial satellite. The Soviets had had a number of other space firsts along the way, and now the Soviet Union launched the first human into space. On top of this, President Kennedy ran in the 1960 election in part on what he perceived as a missile gap between the U.S. and the Soviet Union. He felt that the U.S. had fewer nuclear missiles than the Soviets did, and the U.S. was losing the space race. So on April the 20th, 1961, Kennedy asked Vice President Lyndon Johnson, who was the chair of the Space Council, to study what could be done to close the gap with the Soviet space program. And Johnson responded just 8 days later. Here's a copy of the memo that Kennedy sent to Johnson. And the first question here and we'll read questions 1 and 5. Question 1 is, do we have a chance of beating the Soviets by putting a laboratory in space, or by a trip around the moon, or by a rocket to land on the moon, or by a rocket to go to the moon and back with a man? Is there any other space program which promises dramatic results in which we could win? And he goes on to ask other questions. How much will it cost? Are we working 24 hours a day? And then the last question is, are we making maximum effort? Are we achieving the necessary results? And just 8 days later, Johnson answers. Johnson answers question 1 by saying the Soviets now have rocket capability for putting a multi-manned laboratory in space and have already crash-landed a rocket on the moon. They also have the booster capability of making a soft landing on the moon with a payload of instruments, although we do not know how much preparation they have made for such a project. As for a manned trip around the moon or a safe landing and return by a man to the moon, neither the U.S. nor the USSR has such capability at this time, so far as we know. The Russians have had more experience with large boosters and with flights of dogs and man. Hence, they might be conceded a time advantage in circumnavigation of the moon and also in a manned trip to the moon. However, with a strong effort, the United States could conceivably be the first in those two accomplishments by 1966 or 1967. This is the beginning of the federal funding for the Apollo program. Kennedy's fifth question, are we making maximum effort? Are we achieving necessary results? And Johnson's reply was, we are neither making maximum effort nor achieving results necessary if this country is to reach a position of leadership. So based on this memo, Kennedy consults his closest advisors, and he chose a moon landing as the goal in which the United States would try and beat the Soviet Union. And I think if you think about the timing here, it's really remarkable. The first human is launched into space on April 12th. 8 days later, Kennedy writes to the vice president, to the chair of the Space Council, asking a series of questions. What race can we win? The vice president responds with some choices, one of which is landing a person on the moon, returning them safely to Earth. Kennedy talks to his advisors, and he chooses that one. And as I said, the vice president's response had come just 8 days after that. That was before the U.S. had even launched a human into space. Alan Shepard didn't fly into space on the very first of the Mercury flights, Freedom 7, until May the 5th, 1961. So the United States had not yet even launched a human into space, and Kennedy was already setting a goal of sending humans to the moon before the decade was out. And of course, this would culminate in the famous May the 25th, 1961 speech that President Kennedy gave to a joint session of Congress. Now, this is just 20 days after Alan Shepard's flight. At the point that he's giving this speech, only 2 humans have ever been into space. Only one of them, Yuri Gagarin, orbited the Earth. Alan Shepard was a mere 15-minute ballistic flight up and down. And Kennedy spoke those famous words, of course, and I think even though we saw it in the first lecture, it's worth replaying again because it is such an important part of the history of human spaceflight.
In our time, so as to ensure their fulfillment. I therefore ask the Congress, above and beyond the increases I had earlier requested for space activities, to provide the funds which are needed to meet the following national goals. First, I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space, and none will be so difficult or expensive to accomplish. In conclusion, let me emphasize one point. It is not a pleasure for any president of the United States, as I'm sure it was not a pleasure for my predecessor, to come before the Congress and ask for new appropriations which place burdens on our people. I came to this conclusion with some reluctance. But in my judgment, this is a most serious time in the life of our country and in the life of freedom around the globe. And it is the obligation, I believe, of the President of the United States to at least make his recommendations to the members of the Congress so that they can reach their own conclusions with that judgment before them. You must decide yourselves as I have decided. And I am confident that whether you finally decide in the way that I have decided or not, that your judgment, as my judgment, is reached on what is in the best interests of our country.
So that is the speech that began the race to the moon. So how did NASA do it? We know now, because you've seen in the first lecture, that the first humans set foot on the moon in July 1969, just achieving the goal of landing a man on the moon and returning him safely to Earth before the end of the decade. How was NASA able to accomplish that in less than 8 years? And the answer, frankly, is spending. So in 1961, when Kennedy made that speech, NASA's budget accounted for a little bit more than 1% of the federal budget. If you ask a person on the street today how much of the federal budget goes to NASA, they will usually grossly overestimate the amount of money that we spend on the space program. I've talked to students and to the general public about this, and I've heard everything from 5% or 10% up to claims of that we're spending 25% of the federal budget on NASA. The truth is, in right now, is that NASA's budget is a little bit less than 0.5% of the federal budget. In fact, this year, in 2021, the fiscal year that we're in right now, NASA's budget is 0.48% of the federal budget, just under 0.5%. NASA was able to achieve the goal of landing humans on the moon by 1969 because after Kennedy makes his speech and after Congress decides to fund this, NASA funding rose quickly so that at its peak for a few years in the mid-1960s, it was well over 4% of the federal budget, approaching 4.5% of the federal budget. So the next question then is, how do we reach the moon? The next decision was the mission mode. What technique do we use for getting to the moon? And this was a really important choice because the decision of how to get to the moon would drive the decisions of what kind of rocket was needed, what kind of spacecraft were needed, what kind of lander was needed. Everything depended on what was called the mission architecture. Now, the first proposal, the one that Wernher von Braun was advocating at least initially, was direct descent. Direct descent would send a very large rocket off the surface of the Earth. It would go directly to the moon. That very large rocket would land on the moon. The astronauts would spend some time down on the surface. That very large rocket would take off from the moon. That very large rocket would come back to the Earth, and then a small capsule on the top of the rocket would parachute down to the surface of the Earth. Because the astronauts were taking down to the surface of the moon and returning off the surface of the moon with everything that they were going to need to enter the Earth's atmosphere, this rocket had to be enormous. And in fact, a picture on the left shows roughly what the direct landing type rocket would look like, that it would be huge. There would be a command module on top, there would be a service module below, and then it would require a huge rocket to both land on the surface of the moon and take off from the surface of the moon. So that was one of the options, direct descent. A second choice was Earth orbit rendezvous. And in the case of Earth orbit rendezvous, they would use two smaller rockets, still very large, but smaller than the one that was needed for direct descent, to launch into low Earth orbit initially. One would be the rocket that would take astronauts to the moon and take them home again, and the other one would be all the fuel that was required to fuel that rocket. The problem with direct descent was because you were taking everything with you everywhere you went, it needed a monstrously huge rocket to launch from the surface of the Earth, far, far larger than anyone was even dreaming of building at the time. With Earth orbit rendezvous, you needed a smaller rocket because the rocket going to the moon was going to be launched unfueled. And as we will learn later on, the vast majority of the mass in a rocket is usually the fuel. You could launch the relatively lightweight, unfueled rocket, launch the fuel separately, have them rendezvous in Earth orbit, and then go on to the moon and land on the surface and come back. A third choice that's not shown on here, but I will mention it, is called Lunar Surface Rendezvous. With Lunar Surface Rendezvous, they would send the astronauts to the moon. They would land on the moon in one rocket, but the rocket they needed to take home to come back to the Earth would already be there. That is, that would have been launched uncrewed separately, landed on the surface, and then the astronauts would have to land next to that, spend some time on the surface, transfer over to the rocket to take them home, and bring them home. There were even crazy plans proposed that we could send astronauts to the moon without a real plan to bring them home and just keep sending them food and supplies until we figured out how to get them home. Ultimately, the plan that won was one called Lunar Orbit Rendezvous. The idea behind Lunar Orbit Rendezvous is that you would only take a very small ship down to the surface and back up again. It would not be the spacecraft that you use to survive going from the Earth to the Moon. It would not be the spacecraft that you would use to go from the Moon to the Earth, and it would definitely not be the spacecraft that you would enter through the Earth's atmosphere. This would be a small little excursion ship that would take a quick trip down to the lunar surface and back again. But that meant splitting your crew, because someone would have to stay in orbit around the Moon in the command and service module, while others went down to the surface on this small excursion ship, on this little lunar lander. And that meant that after they lifted off from the surface of the Moon, the two spacecraft had to rendezvous in lunar orbit. Now, this was initially deemed impossible because in the early days, they hadn't even yet accomplished rendezvous and docking in Earth orbit, let alone figuring out how to do rendezvous and docking in lunar orbit. But the great advantage to Lunar Orbit Rendezvous was that the lander was much smaller. It was much more compact for a couple reasons. First of all, you're not bringing everything down to the lunar surface that you need to get home. You're only bringing the astronauts and the supplies that they need for a couple days on the surface. Your parachutes, your heat shield, all those really heavy things that you need to enter the Earth's atmosphere, they stay in orbit around the Moon. All the oxygen and water and everything that you need for the long return journey from the Moon stays in orbit around the Moon. You only bring what you need down to the surface. So this Lunar Orbit Rendezvous, which we all know now from the first lecture is the way that we ended up doing the missions, that was first proposed by Bill Michael, a NASA Langley engineer, and Thomas Dolan, who was an engineer with Vought Astronautics. So both of them independently came up with this idea in which a small lunar lander would descend to the surface. This idea was actually first proposed by Yuri Kondratyuk, who was a Soviet scientist in 1925. But the real reason that this idea won the day was John Houbolt of NASA Langley was the one who proposed that this is the way we should carry out the Apollo programs, with a small lunar lander that would then rendezvous with the command and service module in lunar orbit. So John Houbolt was the champion of this inside NASA management, and this was the architecture that was ultimately selected for the Apollo program. So let's go over what an Apollo mission looked like in general. An Apollo mission in general begins with a launch on the surface of the Earth. Now, you're bringing the command and service module, and they have to be able to sustain 3 astronauts for almost 2 weeks in space. So you're carrying a lot of supplies, all the food, all the water, all the oxygen that they're going to need for nearly 2 weeks in space. Of course, you're carrying the parachutes you'll come home on, the very heavy heat shield. You're carrying the lunar module that you will land on the surface. And this rocket has to give you enough delta V to not only get into Earth orbit, but you actually have to fire that rocket to escape Earth orbit and head off to the Moon. So the rocket that's required would be enormous. And that rocket that was selected, that was designed for this, of course, was the Saturn V. Now, the Saturn V was designed, I should say, by NASA, and it consisted of 3 stages. There was a first stage down here, a second stage, and then a third stage. The first stage was powered by 5 giant F1 engines. They burned liquid kerosene and liquid oxygen as their kerosene was RP1, rocket propellant 1, which is a refined form of kerosene. That was the fuel, and liquid oxygen was the oxidizer. And these 5 F1 engines were the largest, most powerful rocket engines ever built. The second stage right here it was called the S2 stage. The second stage burned liquid oxygen and liquid hydrogen. The third stage also burned liquid oxygen and liquid hydrogen, and it was very confusingly called the Saturn IV-B. The first stage was the Saturn 1C, the second stage was the Saturn II, the third stage was the Saturn IV-B. So just keep in mind when they talk about the Saturn IV stage, they're talking about the third stage, even though it was given the number Saturn IV-B. Sitting on top of the rocket was the lunar module, the service module, and the command module. We'll see those here in a second. But just to give you an idea of how monstrously huge the Saturn V launch vehicle is, here is the Saturn V launch vehicle for Apollo 10 being rolled out to the launch pad. In the background there, you see the the Vehicle Assembly Building. The Vehicle Assembly Building was built specifically for the Apollo missions to the moon. It was large enough that 4 Saturn V rockets could be built and stacked inside the Vehicle Assembly Building at a single time. You can see the monstrously huge hangar doors here that would open to allow the rocket to be transported out on this mobile crawler transporter right here. If you look at the bottom of the transporter, you will see right there these treads that were used to move the rocket out to the launch pad. To give you an idea of how big the rocket is, if you look down here, you'll notice that there's a truck and there's a couple human beings down here. So you can see the enormous size of the Saturn V vehicle. And on this Saturn V vehicle, by the way, the first stage is right here. So this is the first stage coming through here. This is the second stage right here. The Saturn IV third stage right there. The lunar module was tucked in there, the service module, the command module, and then the escape tower at the top. So how would the mission proceed? They would launch from Florida, and they would launch themselves into low Earth orbit. In the process of launching, the first stage and the second stage would be fully consumed, so only the third stage and everything above it would make it into orbit around the Earth. The third stage, the Saturn IVB, is what would eventually propel them onto the moon. But they would spend a few hours in Earth orbit, a couple orbits around the Earth, checking everything out, making sure that the spacecraft was in good shape, because once they fired that engine to leave Earth orbit and head to the moon, they were going to the moon. And so they needed to make sure everything was in good shape before they left. The Saturn IVB fired its engine, that third stage, and that propelled the spacecraft on its way to the moon. Now, this command and service module needed to get the lunar module out of that fourth stage. Now, the command and service module, remember, were the main parts of the spacecraft that kept the astronauts alive. The command module right here is what the astronauts would use to return to Earth. On the bottom of the command module was an ablative heat shield. That is a heat shield that was designed to burn away as they entered through the Earth's atmosphere. Had a docking mechanism up on the top up here so that they could dock with the lunar module. And this is what would sustain the astronauts for the full length of the mission, and it's what they would use to return to Earth. There were parachutes tucked here in the top of the command module. But the command module didn't have enough oxygen or water or other supplies, and so it was attached to the service module. The service module contained oxygen tanks that the astronauts would use for breathing. It would contain the fuel cells that they would use for powering the spacecraft. It contained the SPS, the Service Propulsion System, a very, very powerful engine that burned hypergolic fuels that would be used to slow them down to get into orbit around the moon, and it would be used to fire that engine to get them from the moon back to the Earth. You can also see communications, a series of antennas right here that they use to communicate with the Earth, and then a series of thrusters right there. So this is another picture of what the command and service module looked like. On top of the command module during launch, there is this cover. It's called the Boost Protective Cover, and it sat on top of the command module, protecting the command module from the aerodynamic forces. And then attached to that was, of course, the escape tower. And you'll remember the escape tower was there so that should anything happen during launch, they could fire the escape tower and it would pull the command module away from the disintegrating rocket and save the astronauts' lives. And then you can see everything here inside the service module. All right. So after leaving Earth orbit, very soon after leaving Earth orbit, the command and service module undocked from the upper stage, turned itself around, and came back and retrieved the lunar module, which was tucked inside the top of the Saturn IVB stage. There were 4 panels that were blown off the upper stage using explosive bolts, and then the command and service module moved away from that upper stage, turned itself around, came back, and used the docking adapter on the top of the command module to dock to the top of the lunar module, and then the 2 spacecraft would stay docked together on their transit to the moon. So this is what they would look like on their transit to the moon. So the astronauts in the command module could transfer through the hatch and get into the ascent module of the lunar module, which was the pressurized part of the lunar module. So they would spend a couple days on their transit to the moon. When they got to the moon, the command and service module would fire that giant service propulsion system to slow themselves around to get them into lunar orbit. And once they were in lunar orbit, they would spend, again, about a day in lunar orbit checking everything out, making sure everything was in good shape. And once they were confident that it was, 2 of the 3 astronauts would transfer to the lunar module, and they would take this lunar module down to the surface of the moon. In my opinion, the lunar module is one of the most amazing vehicles ever built. The first thing you'll notice is that it is gangly and unaerodynamic, and that's because it was never designed to pass through the atmosphere of the Earth. This was a vehicle that was designed for working in a vacuum environment. It would land on the surface of the moon, it would take off from the surface of the moon, but it would do all of that, of course, in a vacuum. So it didn't need to be aerodynamic. It didn't need to have a heat shield. And it consisted of 2 parts. The lower part here was the descent stage that carried the large engine that the astronauts would use to descend down to the surface. Of course, it had the 4 landing legs that would stabilize it once it touched down on the surface. It contained all of the equipment that they would need when they were down on the surface, all of their tools, the scientific instruments that they would leave behind. It even contained, as we will see in the later missions, a rover that they could use to drive across the surface. Protruding from the bottoms of the legs right here are the probes that would tell them when they finally touch down on the surface. The top half of the lunar module here is called the ascent module. The ascent module had its own fuel and its own engine, and it would be used to take off from the surface of the moon. In fact, it would use the descent module as its launch pad. The descent module would remain on the surface of the moon, and only the ascent module would come back up. Here's another picture of the ascent module right there. This is on the Apollo 9 mission in orbit around the Earth, where they were testing the lunar module. But I just love this picture because it's a great picture of what the ascent module, what the top half of the lunar module looked like with its ascent engine right there. And here's another picture of the lunar module with its legs tucked up and folded together as it's being installed, literally, in the top of the Saturn 4B, the 3rd stage of the Saturn rocket. And then this is another just line diagram. I love these old NASA line diagrams that sort of show what the spacecraft looked like. So here's the descent module right here. There's the ascent module right there. So the astronauts would take both of these down to the surface, and then this would be the launch pad that they would use to launch from. And then, of course, the lunar roving vehicle. It's important to realize that there was not a rover on every mission. In fact, there was only a rover on the later missions. We'll see that here in a second. So once they were in lunar orbit, 2 of the 3 astronauts would take the lunar module down to the surface. They would spend a couple days down on the surface in the later missions. In the first mission, they would spend less than a day, or about a day, down on the surface of the moon. They would launch in the ascent module. So here we are here. They would go down, they would land on the surface of the moon. They would spend a couple days there, and then they would take the ascent module and they would launch back into orbit, and the ascent module would dock with the command and service module. The astronauts would transfer themselves, the moon rocks that they collected, anything else that they wanted to keep would get transferred to the command module, and they would then discard the lunar module. It was no longer needed, so there was no reason to bring it home. They would then fire the giant engine on the bottom of the service module, that SPS, Service Propulsion System, and they would use that to leave lunar orbit and head back to the Earth. About halfway, they could do a mid-course correction just to get their aim a little bit better. And then once they got back to the Earth, the command module would separate from the service module. The gravity of the Earth would bring it around, and they would aim the command and service module so that they would hit the Earth's atmosphere. That is, they didn't use the service propulsion engine to slow themselves down at all. They just aimed the spacecraft so that the command module would hit the atmosphere and use friction with the atmosphere to slow itself down. And then, of course, they'd parachute down to the surface of the Earth, and the mission would be over. The Apollo program was designed with many different types of missions in mind. The early missions were called, the mission types were lettered with the letters on them. The early missions were going to be uncrewed flights where they were testing out the Saturn V rocket, testing out the command and service module. Then they, like the Gemini program, they would build up their capability. With every flight, they would do more new things so that eventually, by one of the later flights, they would be able to land on the surface of the moon. But they didn't know how many flights it would take, and so NASA originally planned for 20 Apollo missions, with the belief that if the first landing failed, they would try again and again until they succeeded. So these early flights were building up capability. They were testing testing the command and service module, testing the command and service module in lunar orbit, testing the lunar module, doing a dress rehearsal of the first lunar landing, and then, remarkably, the first lunar landing was a success. And so they could then focus more on science on the remaining missions since Apollo 11 was such a success. So let's talk about some of the Apollo missions and their history. And the first one that we need to talk about tragically is the Apollo 1 mission. Apollo 1 was intended to be the first flight of the command and service module. The commander was Gus Grissom. You'll remember that Gus Grissom flew on the second Mercury mission. He flew on the first Gemini mission, and he was widely respected in the astronaut office as one of the best astronauts, and it was believed that he had a very good chance of being the first human to set foot on the moon. The command module pilot was Ed White. Ed White had flown a Gemini mission, and then the lunar module pilot was Roger Chaffee. He was a rookie. He'd never flown in space before. And the goal of this mission was to test the command module in Earth orbit. It would be the very first flight of the command module, and that is a prime assignment for a flight crew to get, the first crew to ever fly a brand new spacecraft. The problem is the command module design and testing was plagued with problems. North American Aviation, who was building the command module, had delay after delay. They had problem after problem. On January the 27th, 1967, they were doing a test of the spacecraft on the launch pad. Now, the rocket wasn't fueled at all. This was just a procedures test, essentially. But they did go through the full procedure of getting the astronauts into their spacesuits, getting the astronauts into the capsule, sealing the capsule. And once the capsule was sealed, it was pressurized at 16 pounds per square inch of pure oxygen. Now, here's the thing to keep in mind. Here on the surface of the Earth, atmospheric pressure is 14 pounds per square inch. So the atmospheric pressure inside the capsule was a little bit higher than the atmospheric pressure that we have here on Earth. But here on Earth, oxygen only accounts for 21% of our atmosphere. In the space capsule, they had pressurized it with greater than atmospheric pressure with pure oxygen. And the test was not going well. The astronauts had spent hours and hours in the capsule. They were plagued by electrical issues. They were plagued by communications issues. Gus Grissom commented at one point during the test, how would we ever get to the moon if we couldn't even communicate with mission control? It was a very, very frustrating day of problem after problem. That evening, as it grew from late afternoon into early evening, a spark underneath one of the astronauts' couches caught a wire on fire. Now, that wire had been soaking in pure oxygen for hours, and it immediately went up in what could be no better described as a conflagration. The inside of the capsule immediately started burning. The three astronauts cried for help, but the hatch on the capsule was so well sealed, and the pressure building up in the capsule was actually pushing on that hatch with thousands of pounds of force that there was no hope that the astronauts themselves could open it. The cry did go out to the mission control teams. They went to the capsule as quickly as they could, but they too couldn't get the door open in time, and all three astronauts were killed in the Apollo 1 fire. The Apollo 1 fire was a disaster. 3 astronauts were killed. They were killed during a test. It wasn't even during a flight. And it was caused largely by the problems that plagued the Apollo command and service module at this time. However, if there is any silver lining to the Apollo 1 fire, it is that it caused NASA to stop and reassess the command module program and begin again and design a new command module. And this time it was designed with fireproofing in mind, and they were able to go through every system. So all the wires, which had insulation that was highly flammable, those wires the insulation was replaced with non-flammable materials. The astronauts' space suits, which in fact had been made of a highly flammable nylon up until that point, they were replaced with a type of cloth called beta cloth that was fire resistant. NASA had to pause, and they had to redesign the command module, and the new command module was known as the Block 2. But after this disaster, after the redesign of the command module, it turned out to be an exceptionally good spacecraft. But unfortunately, it took the Apollo 1 fire to get there. The first launch of the Saturn V rocket happened with Apollo 4 in November of 1967. It was the first full-up flight of the Saturn V. And what's amazing about the Apollo 4 mission is that NASA had the option of testing each of the stages individually. For example, they could test the first stage separately. They could test the second stage. They could test the third stage. They could test the command and service propulsion system. They could test all these things individually. But NASA realized to do that, to test them all individually, would take a long time, and there was no way that they would meet the goal of landing an astronaut on the moon by the time the decade was out. So instead, they decided to do an all-up test. An all-up test meant that they would test everything at one time. They would stack an untested third stage on top of an untested second stage on top of an untested first stage with an untested command module, and they would and an untested service module, and they would test everything in a single flight. This would save a tremendous amount of time, but frankly, it's very risky because should the first stage fail, you would then not get any data on how the second, third, or the command module or the service propulsion system, how any of those performed. So in order to get the full amount of test data, everything had to succeed. Fortunately, the Apollo 4 mission was a resounding success. Now, this was the first ever launch of a Saturn V rocket, and I'm going to play for you the launch. And there's a couple things I want you to get out of this video. The first thing I want you to notice is the Saturn V was incredibly heavy. You might remember earlier in the semester, we did some problems on calculating the acceleration as it's coming off the launch pad, and it's quite slow compared to a modern, much lighter rocket. So you'll notice that the Saturn V lifts off very, very slowly. But the other thing you will remember about the Saturn V is that it burns phenomenal amounts of fuel and oxidizer. These are the largest engines ever made, and 5 of them are burning at the same time, and the noise and the vibration from those are tremendous. So much so that you will hear later in this video Walter Cronkite commenting that the building that they're in is shaking, and in fact ceiling tiles were falling from the ceiling during the launch of Apollo 4.
Spacecraft and all the launch support operations well at time at 90 seconds and counting. Houston flight now confirms that they are go for the flight, as are all other aspects of the mission. T-minus 1 minute, 16 seconds and counting. The pressurization continuing within the vehicle at this time. We also have a hydraulic commit that will permit the hydraulics to drive the engines in the first stage. Liquid hydrogen tank in the second stage now pressurizing. T-minus 60 seconds and counting. T-minus 60. Our status board still shows we're go at this time. T-minus 50 seconds and counting. We have transferred to internal power. The transfer is satisfactory. A 6.2 million pound Saturn V launch vehicle now on its own power at 38 seconds and counting. To repeat, the ignition sequence will start at 8.9 seconds. We'll be looking to lift off at 0. T-minus 30 seconds and counting. We'll count down from starting at T-minus 20. T-minus 25. Stage is reporting ready for launch. T-minus 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9. Ignition sequence start. 5, 4. We have ignition. All engines are running. We have liftoff. We have liftoff at 7 a.m. Eastern Standard Time. The tower has...
My God, our building's shaking here. Our building's shaking. The roar is terrific. The building's shaking. This big glass window is shaking. We're holding it with our hands. Look at that rocket go into the clouds at 3,000 feet. The roar is terrific. Look at it going. You can see it. see it? Part of our roof has come in here.
I've met a number of people who've actually been at Saturn V launches. One of the people, Larry Frederick, a former chair of the astronomy department here at UVA, got to see a Saturn V launch from fairly up close. And they've described the sound from the rocket as being so powerful that it's like somebody pounding on your chest as the rocket takes off. Now, during Apollo 4, they filmed one of the most iconic staging sequences that was ever filmed during the Apollo programs. And what's interesting is this staging sequence is used in many movies. It's used in movies about Apollo 11. I believe it's used in Apollo 13. The thing to keep in mind is that this staging sequence was actually filmed here on Apollo 4. But because most people can't tell the difference between one Apollo rocket and another, they could use this footage in other films. So this is what this first stage coming off looks like. So there's the first stage separating and the second stage igniting. You can see the curvature of the Earth down below. And you'll see the first stage falling away. Now that first stage, of course, doesn't have enough speed to get into orbit, so it's just going to fall down into the Atlantic Ocean. Now, surrounding the second stage here is a skirt, and this skirt will come off in a second, and we will see that come off as a ring. I just love watching that first stage fall away. So the next mission in the Apollo program was Apollo 5, and that was in January of 1968. And so the goal for the Apollo 5 mission, with Apollo 4, they were able to test the command and service module in orbit around the Earth without any astronauts on board. Remember, it was an uncrewed mission. Apollo 5 is an uncrewed mission, and it was the first flight of the lunar module. And this was to test a couple features of the lunar module, in particular to test the descent engine to make sure that it would fire properly, and then to also test something called the fire in the hole. As the astronauts would be descending down to the lunar surface, should they get down close to the lunar surface and have to abort the mission for any reason, they could fire the ascent engine inside the lunar module while at the same moment explosive bolts detached the descent module. The ignition of the ascent module would push the descent module away, but there was some concern about the fact that this engine would be firing into the top of the descent stage, and the pressure might build up and it might damage the ascent module. So they decided to test that in orbit around the Earth. And so they tested this ability of the ascent module to ignite its engine and discard, the ascent module to ignite its engine and discard the descent module and blow it away so that it could abort the mission if necessary. You'll notice on Apollo 5 that the lunar lander did not have its complement of legs. It wasn't going anywhere other than low Earth orbit, and this would all be tested in automatically in low Earth orbit, so it didn't need its landing legs, so they weren't included on the spacecraft on that mission. Apollo 6 was the second flight of the full Saturn V, and the goal for Apollo 6 was to demonstrate the ability to put all this heavy equipment, the command module, the service module, the lunar module, the upper stage here, to put all of that into a trans-lunar trajectory to get it on its way to the moon. Once it went out to the distance of the moon and came back, the command module would then enter the Earth's atmosphere at very high speed, and it would be the first test of the command module heat shield at very high speed like this. Unfortunately, during the launch, they encountered something called pogo oscillations. These are vibrations of the rocket that's brought on by the vibrations of the engines. And it turns out those vibrations happen to match the frequencies at which some of the other components of the rocket vibrated at. And it turns out that fuel lines that fed the igniters in the second stage and third stage were actually broken by this very violent vibration. Because those fuel lines were broken, those engines could not ignite, and in the end, Apollo 6 could not carry out its mission of getting on a translunar trajectory. Nevertheless, they were still able to take the command module, have it enter, not at as high a speed as they wanted, but they were able to test the heat shield on the command module, and everything worked well enough. They understood the pogo oscillation problem and were able to fix it, and that gave them confidence to proceed with the first crewed mission, which was Apollo 7 in October of 1968. So the crew of Apollo 7 was Wally Schirra in the center, Don Isley, and Walt Cunningham. So they were the three astronauts on board the spacecraft. This goal was to test the command and service module in orbit around the Earth for a long duration. This was the first U.S. three-person crew. So, of course, the Gemini missions had two crew members. This was the first time the U.S. flew three crew members at a time. Also, a goal of this mission, one of the highlights of this mission, was the very first ever live television broadcast from space. Now, this mission technically went very well. But in terms of crew-mission control relations, the mission did not go well at all. It began with the fact that all three crew members early in the flight came down with a terrible head cold, and they were suffering with it for the full duration of the flight. Actually, on launch day itself, tensions got high when the wind was blowing in the wrong direction. If the wind was blowing towards the west as the Saturn V launched, as the Saturn rocket, they did not launch, Apollo 7 did not launch on the Saturn V. It launched on a smaller model called the Saturn I. As the Saturn rocket launched, there was concern that if the wind was blowing to the west, that it could blow the rocket back into the launch tower and collide with the launch tower. On the morning of launch, Mission Control thought they were fine. Wally Schirra, the commander, felt that they were not fine, that the wind was blowing too strongly in the wrong direction. But Mission Control won the argument, and they went ahead and launched. But that set up a very contentious mission, a very contentious 11-day mission in space. There were numerous arguments during the course of the mission. Wally Schirra felt that Mission Control was asking them to do too much too quickly. The crew was falling behind in their chores, and it got to the point that even when the crew was asked to do minor maintenance tasks, that there was arguing back and forth between them. It finally all came to a head when it came to reentry. Because the astronauts were suffering from these head colds, they wanted to be able to clear their sinuses. They were worried that on reentry there would be pressure changes, and if they couldn't clear their sinuses, they were worried that they might do damages to their eardrums. So they wanted to do like a diver would do with clearing their nasal passages. But in order to do that, they needed to be able to hold their nose, which meant that they couldn't have their helmets on. So they asked Mission Control permission to not use their helmets during reentry, and Mission Control would not grant that permission. And so in the end, Wally Schirra made the decision to go against Mission Control's desire on this. And they call it the Schirra Space Mutiny. This led to an unfortunate result. Wally Schirra had already announced before the mission that he was planning to resign, that this would be his last flight, and that he was going to retire from NASA. But the other two astronauts never flew again. Isley and Cunningham, this was their only flight into space, and many people believe it was largely because of the poor relations between the crew and Mission Control. So there's the launch of Apollo 7. You'll see that it's not on the Saturn V. It used a different first and second stage down here. Because they were only going to low Earth orbit, they didn't need the full power of the full Saturn V. And then here is the upper stage of the rocket with a docking target so that they could practice docking. They wouldn't really dock with it, but they had a target here that they could use for docking practice. The next mission, Apollo 8, was designed to be a test of the lunar module in low Earth orbit. But the lunar module wasn't ready. Like the command module years before, the lunar module was suffering from delays in design and production. So one option was to just delay Apollo 8 until the lunar module was ready. But there was also indications from the U.S. intelligence community that the Soviet Union was preparing to send an astronaut to the moon, possibly a single cosmonaut in a Soyuz spacecraft to orbit around the moon. They wouldn't have the capability to land that the U.S. knew, but they could send that astronaut around the moon, and this would be another important space first. So NASA decided to take the Apollo 8 mission and change it from a low Earth orbit test of the lunar module into a test where they would take the command and service module and send them to orbit the moon and bring them back. And so this mission took place in December of 1968. The commander was Frank Borman. The command module pilot was Jim Lovell, and the lunar module pilot was Bill Anders. Jim Lovell, of course, would eventually go on to command the infamous Apollo 13 mission. So this goal was to test, now the new goal was to test the Apollo command and service modules in lunar orbit. I would argue that the primary goal was to send the first humans around the moon and make sure that the United States won this first space accomplishment. This was the first crewed launch of the Apollo 5. Because they were going all the way to the moon, they needed the power of the Saturn V, the first crewed launch of the Saturn V rocket. Because they were going all the way to the moon, they needed the full power of the Saturn V rocket. So this was the first time a crew rode the Saturn V rocket into space. And the goal here was, as with a regular Apollo mission, they would orbit the Earth for a few hours, use the upper stage to send them on a translunar trajectory. That means a trajectory to the moon. They would spend a couple days in transit to the moon. They would then fire the SPS system on the service module to slow down and go into orbit around the moon. They would spend a few days in orbit around the moon. They would change their orbit around the moon a few times to test doing that. And then eventually they would fire that giant SPS engine and bring themselves home and parachute back to Earth. They would test much of what would be done on a full-up lunar landing, except, of course, they didn't bring a lunar lander with them. There would be no lunar landing on this mission. And this mission, of course, is famous for the infamous photograph of the Earth rising over the lunar limb that was taken by the Apollo 8 astronauts. For most people, this was the first time they had ever seen a picture of the Earth, essentially all of humanity in one place at one time. And I would argue that this is probably the most influential picture ever to come out of the space program. It's hard to underestimate the influence that this one picture has had. A number of people have made the argument that although the environmental movement was well underway in the 1960s, that this photograph of the fragile Earth by itself above the lunar limb, letting people realize that our planet is just a tiny little planet in the vast universe, helped spur on some of those environmental efforts. The next mission was Apollo 9, and Apollo 9 was in low Earth orbit. It never went to the moon. The goal here was to do a full-up test of the lunar module with astronauts on board. So the commander was James McDivitt, the command module pilot was Dave Scott, and the lunar module pilot was Rusty Schweickart. So they were going to test the lunar module in low Earth orbit. They were going to test docking and rendezvous with the lunar module. They were going to fire the lunar module engines. They were also going to test the extravehicular mobility unit, the backpack that the astronauts would eventually wear on the surface of the moon. So Apollo 9 launched again, low Earth orbit, never went to the moon. So here is the upper stage of the Saturn V rocket. Again, since they weren't going to the moon, they didn't need the full Saturn V, but there's the lunar module sitting inside that upper stage. Here is Rusty Schweickart coming out of the command module, doing a spacewalk over to the lunar module. This spacewalk turned out to be in a bit of danger of not happening. It turns out that Rusty Schweickart was the first U.S. astronaut to suffer from space adaptation syndrome, essentially motion sickness. Rusty Schweickart had a very bad case of it. The first few days he was in space, he was nauseous, he was throwing up all the time. At first, after he threw up the first time, McDivitt didn't think it was worth mentioning to Mission Control, but after he threw up a few more times, they did have to mention it to Mission Control. There was talk about canceling the spacewalk that Schweickart was supposed to do because they were afraid that if he was trapped inside of his spacesuit and he were to vomit inside the spacesuit, There'd be no place for that vomit to go, and he might aspirate it, breathe it in. But it turns out by a couple days into the mission, his system had settled down, and Rusty Schweickart was able to recover, and he was able to do the spacewalk. And then here's a picture of the lunar module in orbit around the Earth. And then, as we already saw here, the ascent stage of the lunar module. So they practiced firing the descent stage, they practiced separating the descent stage from the ascent stage, and then firing the engine on the ascent stage as well. One thing I will say about Rusty Schweikart's space sickness is that we know now that that is not unusual. That space adaptation syndrome is a very common aspect of traveling to space. They just didn't understand that in the early space program. And because of that, Rusty Schweickart never flew in space again. NASA felt that there was something wrong with him physiologically and that it wasn't safe to fly him if he was going to get sick like this. We now realize, after over 100 space shuttle missions, that space sickness is a real problem that many people suffer from, but it's easy enough now that we know about it to recover from it. And Gene Cernan once said that when it came to understanding space sickness, Rusty Schweickart paid the price for them all. So his career suffered because they didn't really understand what he was going through at the time. All right, Apollo 10. Apollo 10 was the first dress rehearsal for the first lunar landing. It took place in May of 1969. The commander was Tom Stafford. The command module pilot was John Young, and the lunar module pilot was Gene Cernan right here. This would be John Young would go on to command Apollo 16, and Gene Cernan would go on to command Apollo 17. So this was a full-up dress rehearsal for Apollo 11. They did everything except land on the moon. But they took a Saturn V rocket. They went all the way to the moon. They orbited the moon. They took the lunar module down to a few tens of thousands of feet above the surface of the moon. They then separated the descent stage. They fired the ascent stage, went back up into orbit, docked with the command module, came back home. They did everything but land on the moon with the Apollo 10 mission. So that set the stage for the first lunar landing, Apollo 11. The question is, where would they land on the surface of the moon? So a couple of things I want to mention about the moon right now before we go to the lunar landings is that the surface of the moon consists of two types of terrain. There are these really heavily cratered regions called the highlands, and these really smooth regions called the maria on the moon. The highlands are places that are very, very old. That is, the rocks here have been exposed to space for a very long time. And we know that because they're completely covered in craters. The maria, on the other hand, are much younger. Now, you might wonder, how can some parts of the moon be young and some parts of the moon be old? Well, remember, it's just like the surface of the Earth. The Earth has been geologically active. Mountain ranges on the Earth have different ages. The Appalachian Mountains are very old. The Rocky Mountains are very young. The moon used to be geologically active as well. And so the surface of the moon was being changed over time by these geological processes. And just by looking at the moon, you can tell which regions are young and which regions are old. Now, these maria on the surface of the moon, what were called the seas on the moon, they were called the seas long ago because when the first astronomers looked at them, they noticed that they were smooth and dark and flat, and they thought they were filled with water, so they called them the seas, or the Italian word, the mare for sea. And they were given Latin names like Mare Serenitatis, the Sea of Serenity, or Mare Tranquillitatis, the Sea of Tranquility, or Mare Fecunditatis, the Sea of Fertility. The highlands, on the other hand, as I mentioned, are very heavily cratered. They are literally craters on top of craters on top of craters. And they've been exposed to space for a long time. And because they've been exposed to space for a long time, they've been badly battered by comets and asteroids and meteoroids striking the surface of the moon. But the lava flows are much younger. This is a picture of the Mare Imbrium lava flow. And because they're much younger, they haven't been battered nearly as much by comets and asteroids and meteoroids. So the surface of the lava flows are largely intact. For example, with this lava flow, you can actually see a frozen lava flow right here. You see what looks like a river channel, and that is in fact frozen lava. It froze billions of years ago on the surface of the moon, but you can actually see where the lava was flowing across the surface of the moon. Now, the lava on the moon is very much like basaltic lava that we have here on Earth. This is the Big Island of Hawaii. And if you've ever traveled to the Big Island of Hawaii and gone to Volcanoes National Park, you've seen lots and lots of basaltic lava. It is of the two main types of lava. It is the thinner lava. It flows more freely. In fact, you'll see here, you can see where the lava just flowed down this hillside right here, and it's just lightly draping the hillside as it flowed and pooled down here. Basaltic lava is the runnier, as I said, of the two types of lava. It's also very dark in color, almost black in color. And that is why the lunar seas are darker than the highland regions, because they're filled with this lava. Now, another thing you'll notice about the lunar seas is that most of them are round in shape. And the reason that they are round in shape is when that lava came up from underneath, came up through cracks in the lunar surface up to the surface of the moon. When it came up from underneath, it filled in the bottoms of giant impact craters. So the Sea of Serenity used to be a giant impact crater that then filled in with lava. And we differentiate the crater, we call it a basin in astronomy, from the lava that filled it in later. Probably the most famous of these, of course, is Mare Imbrium, the Sea of Showers right here. We call the giant crater right here, which is almost 800 miles across, we call that crater the Imbrium Basin. And we call the lava that flowed in to that basin, we call that Mare Imbrium, the Sea of Showers. So let's talk about the first landing on the surface of the moon, Apollo 11. Now, I talked extensively about it in the first lecture, so again, I'm just going to very briefly talk about what happened. The commander was Neil Armstrong. The lunar module pilot who would go down to the surface with Neil Armstrong was Buzz Aldrin. The command module pilot who would stay in orbit around the moon in the command and service module was Michael Collins. So this was the first lunar landing, landed, of course, on July the 20th, 1969. They had a single extravehicular activity that lasted about 2.5 hours. The question was where they would land on the surface of the moon. For a variety of orbital reasons and the fact that the moon pretty much sits in the Earth's orbit around the sun, they would have to land someplace close to the lunar equator. They could not land at very far north or very far south latitudes. So the first landing would have to be someplace close to the lunar equator. For technical reasons, they wanted to be on the east side of the moon. And that was so that if the launch was delayed, and they had to delay for a few days, they could move the landing point further west. That was one of the reasons. So it had to be on the east side of the moon. And of course, they wanted to be in one of these smooth mares, one of the smooth maria, the seas of the moon that weren't completely covered in craters. The terrain was much smoother, much flatter, and would make for a much safer landing. So close to the equator, on the east side of the moon, on one of the seas, eventually meant that they picked a landing site in the Sea of Tranquility, Mare Tranquillitatis. It's on the very southern, southwestern corner of the Sea of Tranquility. This is the Sea of Tranquility up here at the top. This is the southwest corner. There is this half-buried crater right here, so it looks like looks like the sort of the face of an owl with the two ears. There's the two horns sticking up right there. That is actually the rim of a crater, but the crater is half buried under the lava. If you ever use a telescope to look at the moon, you can find the Sea of Tranquility. You look in this southwest corner, find these two little horns, find the left horn, go north a little bit from there, and that's the Apollo 11 landing site. Of course, you're not going to see the spacecraft from Earth. They're much too small, but that's where the landing site was. About a day before landing, as they were in orbit around the moon, the astronauts got their first look at the landing site. So that arrow marks where the landing site was located on the moon. They specifically chose to land on the landing site right after the sun rose at that time. There were a couple reasons for this. First of all, when the sun just rises up, all the craters and rocks and everything on the surface cast long shadows. That makes them easier to see, makes it easier to see the terrain. The second reason is when the sun is not very high in the sky, the lunar surface is not very hot. The sun is not doing an efficient job of heating the lunar surface, and so the spacesuits would not have to work as hard to keep the astronauts cool. By the time lunar noon comes around with the sun high in the sky, the surface temperature is well over 200 degrees, and the spacesuits would have to work very, very hard to keep the astronauts cool. So they selected early lunar morning. And here's another picture of the landing site from orbit. You can see that it is a fairly smooth nondescript region. Not a lot of craters on this part of the moon. And you can go back and watch the first lecture again if you want to find out what happened on the surface of the moon. I talk in detail about their extravehicular activity, their traverse, where they spent a little less than 2.5 hours outside. Here's a picture, of course, of Buzz Aldrin saluting the U.S. flag on the surface of the moon. You can see their footprints here on the surface of the moon. Here's Aldrin removing some of the scientific equipment out of the descent stage of the lunar module. And this was the experiments package that they would end up leaving behind on the surface. That you might remember, this first package had a seismometer and it had a retroreflector that could reflect laser light so we could measure the distance to the moon. And then, of course, after the lunar walk on the surface, they went back into the lunar module. They took a rest for a while, weren't able really to sleep. They were too excited, so they rested for a while before eventually using the ascent module to come back into orbit, joining Michael Collins in the command module Columbia, and then spending another day in lunar orbit there, and then discarding the ascent module. It would eventually crash down to the lunar surface on its own, and using the giant service propulsion system to send themselves back to the Earth. And you'll remember for Apollo 11, once they landed on the Earth, they had to go into a period of quarantine because we weren't confident that we were confident that they wouldn't, but we weren't sure. There was a remote possibility that they would bring back bacteria or viruses from the moon, and we didn't want to contaminate the Earth with those. And so the astronauts decontaminated themselves inside the spacecraft. They put on contamination suits, and then they spent a couple weeks in the isolation trailer to quarantine themselves until we were sure that they weren't infected by anything. In fact, here's a famous picture of the 3 astronauts on the USS Hornet, and there they are in the quarantine trailer, and that's President Nixon congratulating them on their mission. So what did we learn from this first lunar mission? The first thing we learned was about the lunar regolith, the soil or the dirt that's on the surface of the moon. It's not organic dirt like we have here on Earth. It's actually made up of crushed and broken rock. It's very fine, very powdery, very fragmental. It's been weathered by billions and billions of collisions with small particles hitting it. It's been moved around and transported by larger things hitting the surface and blowing the particles across the surface. Interestingly, at the very end of his moonwalk, Neil Armstrong was packing up the boxes, full of rocks, and he noticed that they were empty, that there was a lot of space between the rocks. And in a brilliant move, he decided to use a shovel, and he just shoveled in a whole bunch of this regolith on top of it. He figured the scientists wouldn't mind having more samples, and it turned out that was a very valuable thing to do, to get a large quantity of that regolith that scientists could study. And what we found is that this fine fragmented material here on the surface, most of it comes from the local bedrock. That is, this fine fragmented material, this crushed and broken rock, this powdery material that's on the surface, it's probably about 5 meters thick, about 15 feet thick. And underneath it is the bedrock. And most of this fine powdered material consists of the bedrock material. Some of it is types of rocks that come from the lunar highlands, and that means that these samples, about 3% of the total sample, had to come from more than 100 kilometers away. So these are where an impact happens 100 miles or more away, hits the surface, and it blows material that lands in this area that then gets mixed in with all that regolith. And some of it was also fragments of glass that came from volcanic activity on the surface of the moon. So that was the soil on the surface, the regolith. Of the lunar samples that they brought back, about half of them were crystalline igneous basalt rocks. Not surprising. We knew they were landing on a lava flow, and about half the rocks that they brought back were igneous basalt. They recorded 2 different kinds of basalt. They were 3.65 billion years old, which is remarkable because that is much, much older than surface rocks on the Earth, because the Earth has been geologically active through that time. So lots of rocks on the Earth have been weathered and worn away. These are incredibly old. And these lava flows occurred over a time period of about 170 million years, but they happened 3.65 billion years ago. We also learned from these early rocks that there were no volatiles in the moon, in the rocks on the moon, or very few volatiles. Earth rocks are filled with lots of water, and lunar rocks had essentially no volatile materials like this, which meant that they were heated at some point to very high temperatures, and that led to the idea that the moon was actually formed when a Mars-sized body struck the Earth and blew the material into space. All right, Apollo 12, the next lunar landing, landed on the Ocean of Storms, November 14th to the 24th, 1969. The commander was Pete Conrad. The command module pilot was Dick Gordon, and the lunar module pilot was Alan Bean. One of my favorite Apollo crews because the three of them were very good friends. They got along with one another, great practical jokers. One of the goals of Apollo 12 was to demonstrate the ability to do a pinpoint landing. You'll remember that coming in on Apollo 11, Neil Armstrong determined that they were going to land well beyond their designated landing site. In fact, they ended up landing miles beyond their designated landing site. It was a problem on Apollo 11, not a disaster, but it was a problem. He certainly had to spend much more time landing than they thought. But future missions would be landing next to large mountain ranges, and there was even a plan to possibly land in one of the giant craters on the moon. And if they were going to do that, they needed to be able to do a pinpoint landing. If you're landing next to a mountain and you're miles off course, you could crash into the mountain. So the goal for Apollo 12 was to land next, to do a pinpoint landing. And the place they decided to land was a place that we had been to already. About 2 years or a little more than 2 years earlier, the United States had launched a robotic spacecraft to the moon called Surveyor 3. And Surveyor 3 landed in the Ocean of Storms, and they decided that the perfect way to prove a pinpoint landing was to get Apollo 12 to land next to Surveyor 3. This would not only demonstrate the pinpoint landing, but it would allow them to cut pieces off Surveyor 3, bring them home, so that we could determine the long-term effects on space hardware. Because here's something that had been sitting on the surface of the moon for more than 2 years, and so we could bring it back and see what the effects of spaceflight had on that equipment. They would also deploy an experiment package on the surface, and for the first time they would obtain documented samples. Apollo 11, they were in such a hurry that they were able to gather rocks off the surface, but they weren't able to document them very well. The goal of a documented sample is that you photograph the area around the rock. You photograph the rock precisely how it's sitting on the surface. You document exactly how the rock was sitting, then you sample it, then you bring it back to Earth. And that context tells geologists a lot of information about that rock. And that was lacking from Apollo 11 because they just didn't have the time in that mission to do the documented samples. They ended up doing 2 extravehicular activities, a total of 7.5 hours. They walked about 2 kilometers on the surface of the moon, and they brought back 34 kilograms of samples. So they landed right on the edge of Surveyor Crater. In fact, right after they landed, Alan Bean was able to look out the window of the lunar module, and he was able to see on the other side of the Surveyor Crater, was able to see the Surveyor 3 spacecraft just coming out of the shadows of the Surveyor Crater. So they were quite excited that they carried out their pinpoint landing. In fact, you can see from this photograph that Surveyor 3, it was known, was sitting on the edge of a giant crater. You'll notice that Alan Bean Pete Conrad. Pete Conrad put the lunar module down right on the edge of that same crater. So there it is. You can see the edge of the crater. They're sitting right on the edge of the crater right there. Their first extravehicular activity, they deployed the experiments package. They walked over to Middle Crescent Crater. Their second lunar excursion, they did a walk around Head Crater, around Bench Crater, out to Sharp Crater, came back and visited the Surveyor 3 spacecraft. Here they are deploying the Apollo Lunar Surface Experiments package. These were experiments that were left behind on the surface of the moon. And then this is them visiting the Surveyor 3 spacecraft. So you can see on the other side, here's the Surveyor Crater, as it's called. There's the Apollo 12 lunar module on the opposite side of the crater. And then there's the lander itself. One of my favorite stories that comes out of the Apollo program is the practical joke that Alan Bean and Pete Conrad were going to play with Surveyor 3. Right before the mission, they had sent a colleague to go to a local camera store and buy them a small mechanical timer that they could connect to one of their Hasselblad cameras. The Hasselblads were the cameras they were using to take pictures on the surface, and they'd hatched this plan that with the timer attached to the camera, they would be able to use the camera mounted on a tool carrier that they had, and then both of them would be able to stand next to the Surveyor spacecraft and photograph themselves next to the Surveyor spacecraft. The mechanical timer was literally just a mechanical device that you could set, and then it would tick away for a few seconds and then take the photograph, very much like the electronic timers we have on our cell phones today. So they had this plan. They walked all the way around on this second EVA. When they got to Surveyor, they looked in the bag full of rocks where they had stored the timer, and they couldn't find the timer because there were so many rocks in the bag. In fact, they told Mission Control that they needed to take a break, and while they told Mission Control they were taking a break, they were actually unloading the rocks out of the bag, looking for the timer in the bottom of the bag. And as hard as they looked with all the dust and dirt and rocks in the bag, they couldn't find the timer, and they gave up on their plan. They ended up not being able to take the photograph. Eventually, at the very end, when they were packing the rocks in the metal boxes to come home, they did find the timer in the bottom of the bag, and they were so frustrated that they took the timer and they threw it away. So it's still sitting on the surface of the moon. After the mission, Alan Bean became a painter, and Alan Bean painted one time, one of his famous paintings is The Fabulous Photo We Never Took. Alan Bean and Pete Conrad standing in front of Surveyor 3 with the camera mounted on the tool carrier, so he was able eventually later in life to paint the picture that they never got. So what did they determine from Apollo 12? Well, they were able to dig a trench, and inside that trench they discovered some lightly colored material that they believe came from the crater Copernicus, and they were able to use that material to determine that Copernicus, one of the youngest, freshest craters on the moon, is 810 million years old. And by Earth standards, that's ancient. And yet on the moon, that's one of the youngest, freshest craters. Of course, the next mission was Apollo 13 from April 11th to April 17th. Later in the semester, I will have you watch the movie Apollo 13. The commander was Jim Lovell. He'd flown in Gemini. He'd flown on an earlier, the Apollo 8 mission. Now he had the chance to command a mission. The command module pilot was Jack Swigert, and the lunar module pilot was Fred Hayes. So the goal here was to land on the Frau Mora formation. I'll talk more about that in a few minutes with Apollo 14. But of course, Apollo 13 is famous for the accident that occurred 55 hours into the mission. 55 hours after leaving the Earth on their way to the moon, they had an explosion of one of the oxygen tanks on board. And that imperiled the lives of the astronauts. And as you will see from watching the movie, working with Mission Control, the Apollo 13 astronauts were able to save the day. They were able to move over to the lunar module, use the lunar module as a lifeboat, use that to survive long enough to swing themselves around the moon, come back, return to Earth, and land on the Earth. Of course, as the movie very well demonstrates, the lunar module was only designed to keep 2 people alive for a couple days. Now it was going to have to keep 3 people alive for many days. So lots of conservation had to go on. They had to conserve water. They had to conserve power. They were under very difficult conditions for most of that return. Even though you might think of this explosion as being a failure, NASA looked at it as one of their great successes because NASA, under very difficult, trying circumstances, was able to bring the crew home successfully. This is a photograph of the service module after the command module undocked from it, and you can see the side blown out. There was a metal panel that covered this side. It turns out that oxygen tank exploded, and the Apollo 13 investigation revealed that that tank had been mishandled. But interestingly, what they revealed is that accidents in spaceflight, accidents in commercial aviation, are usually not just a single cause. There's usually multiple things playing a role at the same time. So what happened in this case was that the oxygen tank that was being used, inside of it was a thermostat. And that thermostat was designed to be operated at 28 volts. That was the voltage that they would be using when the spacecraft was in orbit. What the maker of the thermostat never knew was that when they were doing ground tests, when the spacecraft was hooked up to ground power instead of the power they would have in space, they used 65 volts instead of 28 volts. And the thermostat maker never knew that, so they didn't design the thermostat to operate under the higher voltage. Now, it had flown like this on many Apollo missions before, so that wasn't the issue. A second thing happened was that there were 2 oxygen tanks inside the service module. In October of 1968, tank number 2 was dropped, and it was only dropped by a couple inches, not very much. They looked at the tank, it was only dropped a couple inches, it appeared just fine, so they mounted the tank inside the spacecraft and decided to use it. Well, they were doing a countdown demonstration test where they fully load the tanks full of oxygen, and one of the 2 tanks of oxygen wouldn't drain out. When they were trying to figure out why it wouldn't drain out, they realized, oh, that was the tank that got dropped. And they realized that the little drain valve, there was a little tube inside that would be used to drain it. Maybe that tube had gotten bent during the dropping. So the engineers decided that the way they would drain the tank, that they would get the oxygen out of the tank, is they would just turn the heaters on inside the tank. The heaters would cause the oxygen to boil away, and then the thermostat would eventually shut the heaters off when all the oxygen had boiled away. The problem was they were on the ground, and the thermostat was operating at 65 volts, and those 65 volts shorted out the thermostat, which meant the heaters never turned off. The temperature inside the tank rose to 1,000 degrees Fahrenheit, but nobody noticed because the temperature gauge attached to the tank didn't go that high. And because it never went that high, nobody knew that the inside of the tank got up to 1,000 degrees. Well, that damaged insulation on the wires. But remarkably, they were able to fill that tank with liquid oxygen, and it was able to make it 55 hours to the moon before they lit a fan or turned power to a fan to circulate the oxygen in that tank. And when they circulated the oxygen, a spark caused a fire inside the tank, which caused that, and of course that spark, because it was inside a tank of liquid oxygen, that fire was fed by pure oxygen, and that resulted in the tank exploding. So there wasn't a single cause for the problem. There were multiple issues involved. And we'll see that over and over again in spaceflight. When an accident occurs, it's usually not a single cause. Well, Apollo 14 picked up where Apollo 13 was supposed to go. In January to February of 1971, by the way, you'll notice that Apollo 13 was in April of 1970. Apollo 14 was in January of 1971. So NASA recovered from this, was able to redesign the oxygen tanks on the command module, move them around, and do all of this in a period of less than a year before we had the next mission to the moon. That was Apollo 14. The goal here was to land on the Frau-Mora Formation. The commander was Alan Shepard, the first American to fly in space. This was his second space flight. He had been grounded because of troubles that he was having with his ear that were eventually solved by surgery. The command module pilot would be Stu Roosa, and the lunar module pilot who would go down to the surface of the moon with Al Shepard was Edgar Mitchell. Their landing site was over here in the Ocean of Storms. You'll remember I mentioned Mare Imbrium, the Sea of Showers here, sits inside of a giant impact crater. Scientists wanted to know how old that impact crater was, and to determine how old it was, what they wanted to find was material that splashed out of the crater when the crater was made. And that material is this little streak of material down here, and because the crater Frau-Mora sits on top of it, it was called the Frau-Mora Formation. And the Frau-Mora Formation is literally just rocks that were thrown out of the Imbrium Basin that came crashing down to the moon and coated the surface of the moon. By landing on these rocks, of course were molten when they were splashed out of the crater. By landing on those rocks, they could sample that material that was splashed out of the Imbrium Basin and determine how old the Imbrium Basin was. Now, in order to do that, they needed to find material that specifically came from the Frau-Mora Formation. So they decided to go to a young, fresh crater, because craters do astronauts a huge favor. A crater excavates the local material and brings it to the surface. When you look at young, fresh craters on the moon, they're surrounded by rocks, and those rocks came from the local area. If you see a rock sitting on the moon in isolation, you don't know whether it was blown out of a local crater or whether it came from a long distance and maybe landed there. But when you see lots of rocks around a young, fresh crater, you can be confident that most of those rocks came out of the crater, and the crater is excavating the local material. So if you want to know what the Frau Maurer Formation is made of, you find a young, fresh crater. In this case, its name was the Cone Crater, with all the young rocks around it. Now, this crater was about 1,000 feet across, 370 meters in diameter, and it was on a ridge that they had to climb from their landing site. And as I said, Cone should have penetrated through the regolith and this crushed and broken stuff on the surface and thrown up bedrock, thrown up unambiguous pieces of the Frau Maurer Formation to the surface. Many people would argue that this was the most important spot that astronauts visited on the surface of the moon. The problem is, when they landed, the terrain was undulating, and from where the astronauts stood looking up at this ridge, which was the flank of Cone Crater, they couldn't determine where the rim of the crater was. The astronauts started walking up the side of the crater, and the goal was to sample rocks that came right from the rim of the crater, because those would be taken from the deepest depths down inside the crater. But they got lost. They wandered off. And in fact, Al Shepard believed they should go one direction. Edgar Mitchell believed they should go the other direction. They eventually went where the commander wanted. But it turns out, instead of walking towards the rim of the crater, they were walking parallel to the rim of the crater. They never reached the rim of the crater, which is a shame, because I would love to see the photograph that they would have taken standing on the edge of a crater that's 1,000 feet across. That would have been a spectacular photo. It turns out they did get within 17 meters, within about 50 feet of the rim of the crater, and they did sample a large rock that they found there. But the scientists had hoped to get many samples from the rim of Cone Crater, and they ended up getting just one large sample, sample number 14321, which came from the rim of Cone Crater. What they were able to determine from that is that the Imbrium Basin itself, that giant impact that blew that giant crater that the lava eventually filled in, it was between 3.82 to 3.85 or 3.87 to 3.96 billion years. And it's widely assumed that that younger age, 3.82 to 3.85 billion years old, dates the creation of the Imbrium Basin. From how long the rocks had sat on the surface, they were able to estimate that Cone Crater, that young, fresh crater, it was about 25 million years old. The next mission to the moon was Apollo 15, July to August of 1971. And the goal here was to land in the Sea of Showers. The commander was Dave Scott. The lunar module pilot was James Irwin, and the command module pilot was Al Worden. So Scott and Irwin went down to the surface. The landing site was a landing site that has one of my favorite names on the moon, Palus Putridennis, or the Putrid Swamp. And they landed on July the 30th, 1971, and had a total of 3 extravehicular activities, and this was the first mission with a lunar rover. The goal here was to land next to the Apennine Mountains, right at the base of this giant mountain range that was created when that crater was made. This would allow them to sample material that was probably brought way up from underground as this crater was made, as this giant body, a body that was probably about 80 miles across or so, striking the moon, blowing this huge crater. As it blew this crater, lots of material would be blown out of the crater and land on the surface, and some of the stuff that came from the deepest layers would have landed right here on the rim. So Apollo 15 went to go investigate these mountains because it would find material that came from deep underground, but it would also allow them to travel. They would land on the surface of the sea and sample that material, drive up into the mountains with their rover, sample that material. I think the most spectacular landing site of any of the lunar missions. So here are the Apennine Mountains, the rim of that giant Imbrium Basin on the surface of the moon, and this is the landing site nestled right up against the Apennine Mountains. They landed on the surface of the lava, but with their rover they were able to drive up into the mountains to sample the mountains. They were able to sample the lava, and there was also this lava rill, a place where the lava used to flow across the surface, and they were able to drive over and investigate that on their 3rd EVA. Here's what the landing site looks like in detail. There's the landing site. On their first 2 EVAs, they ended up exploring the mountains over here, and then on the 3rd EVA, they went and explored the lunar rill. And here's one of my favorite Apollo panoramas showing the lunar module Falcon sitting on the surface of the moon with the Apennine Mountains in the background. Just a spectacular view with the mountains. One of the astronauts working there, and of course, their lunar rover. So, as I said, the astronauts were able to drive up into the mountains. They did it twice. Actually able to drive the lunar rover right up onto the edge of the mountains. They had hoped that with this giant St. George crater here that they would find lots of rocks on the side of the mountain. They also visited a small crater here called Spur where they hoped to find more rocks. And they were really surprised to find out that the flanks of the mountains didn't have nearly as many rocks as they hoped. But on the edge of Spur crater right here, they did pick up one rock, and its name is the Genesis rock. It's rock sample 15415. It's a piece of the original lunar crust. It's about, it's over 4 billion years old, and it is the oldest rock ever returned from the moon. And it's, as I said, it's believed to be a part of the original lunar crust. So it was well worth the Apollo 15 missions to drive up into the mountains. And there they are on the edge of that rill, collapsed lava tube. You can even see inside that lava tube, you can see layers where the lava flowed at different times. So that Genesis rock was dated at 4.15 billion years old. It turns out its age was reset at some point. It could be even older than that. But that was the most important sample that came back from Apollo 15. The Apollo 16 mission was to land for the first time in the Highlands, the heavily cratered Highlands. The commander was John Young. The lunar module pilot was Charles Duke, and the command module pilot was Ken Mattingly. You'll see in the Apollo 13 movie that Ken Mattingly was originally supposed to be on Apollo 13, but because he was exposed to measles, he was switched out. The landing site here was to look in the lunar highlands down here. And if you look at these lunar highlands, there are smooth regions in the lunar highlands. So, right, the lunar highlands are very rough, they're very heavily cratered, but there were these occasional smooth patches. And the belief was that this represented some kind of volcanic activity in the lunar highlands. So by landing on these regions, these places with volcanic activity, they could not only sample the volcanic rocks, but again, drive up into the mountains and sample the lunar highlands. So Apollo 16 landed between 2 mountain ranges. There was Smoky Mountain to the north, and there was Stone Mountain to the south, and they would land on this smooth area in between and sample what they thought was a lava flow. When they got to the moon, right away, they looked out on the surface and they could tell that they were not sitting on the surface of a lava flow. John Young commented, looking out the window of the lunar module before they ever went out into the surface, that it looked to him that most of the rocks they could see were highland rocks, crushed and broken rocks called breccia, where rocks had been cemented together from other pieces as they've been hit and pummeled time after time again. It turns out this mission showed very well the limits of being able to take photographs from space and tell what's going on down on the surface. It was believed that these smooth areas, like the other smooth areas where the astronauts had landed, would be a lava flow. Instead, it turned out to probably be molten material that was splashed out in the impact of the Imbrium Basin. This impact was so violent that not only did it splash material here at the Frau Mora Formation, but it splashed material that made it all the way over here to the Apollo 16 landing site. And what we're looking at, this smooth material, is probably fluidized ejecta, fluidized rock that was crushed and broken and heated to such a point that it flowed like a liquid, filled in all these low-lying areas, and it made it look like a lava flow when in fact it was just ejecta from the Imbrium Basin. So that was the primary result that came out of Apollo 16. They found that all the rocks were breccias. None of them were consistent with a volcanic origin, and this showed the limits of photogeology, being able to take pictures and determine what's going on. All right, the last mission to the surface of the moon was Apollo 17. The commander was Gene Cernan. He had flown, you'll remember, on an earlier Apollo mission. The command module pilot was Ron Evans, and the lunar module pilot was Harrison Jack Schmitt. Jack Schmitt was substituted in for another astronaut here because Jack Schmitt turns out to be the only scientist that got to fly to the moon. He had a PhD in geology and was selected for the astronaut corps, but he was a bit of an outsider in the astronaut corps. The astronaut corps consisted largely of test pilots that came from the U.S. military. And here was an academic, someone who had earned a PhD in geology and didn't have the same flying credentials as everyone else. But under political pressure, it was decided that we had to send a scientist to the moon. And so Jack Schmitt substituted for another astronaut on the Apollo 17 mission. Their goal was to visit the Taurus-Littrow Valley on the edge of the Sea of Serenity in December of 1972. In particular, there were a number of craters in this vicinity that had dark halos around them, and it was thought that these dark halos represented a type of very recent volcanism. Maybe this would be the last gasps of the moon before the volcanoes finally shut down, because, of course, just looking at the moon today, there are no active volcanoes, and it's clear that volcanoes have not been active on the moon for a very long time. So the goal was to go to the Taurus Mountains and look at the lava flows, the sea that was right below the Taurus Mountains where these volcanic flows might have occurred. So the Apollo 17 mission was on the southeastern edge of the Sea of Serenity right here in a group of mountains called the Taurus Mountains. Even on this photograph, you can notice that there's a little black spot right there. The Maria there were a very different color than the Maria in other ages, and it was believed that over time they fade from very dark black to a lighter gray, and that's why that landing site was selected. And you'll notice that the lava flow here that goes in and between the mountains is very dark in color, and that was the selected landing site. Here are the Taurus Mountains, and then there's the landing site right between the Taurus Mountains. This is what it looked like from orbit. So the landing site is down here on the bottom of the valley. But again, having a rover would allow them to drive up and sample the mountains, but also sample the valley floor itself. One of the most important discoveries in the Apollo 17 mission was on one of the EVAs. Harrison Schmitt was walking along, Jack Schmitt, and he turned up soil, and when he looked down at his boots, he noticed that the soil was distinctly orange in color. It created a tremendous amount of excitement, and it turns out that this orange soil came from little glass beads in the soil. It came from a very active fire fountain. This is what volcanic activity does. When magma is thrown up at very high velocities, it can create a huge fountain, and as that stuff fountains out, the material cools very quickly, forms a glassy deposit, and that orange soil came from all these little glass spherules that were in the regolith. They were also able to visit a number of large boulders on the surface. The samples from the mountains, the massifs as they were called, dated the Serenity Basin at about 3.86 to 3.87 billion years ago, roughly the same as the Imbrium Basin. The basalt that flowed on the floor was a little younger at 3.7 billion years old. The orange soil that I talked about came from those little glass spherules, and it turns out that they are actually about 3.6 billion years old, so it was not young volcanoes on the moon. I mean, think about these numbers for a second. These volcanoes essentially stopped operating about 3.6 billion years ago on the surface of the moon. 3.6 billion years old, that's as old as the surface rocks, the oldest surface rocks on the Earth. Some of the youngest volcanism on the moon, that is, the most recent volcanism, is older than the oldest rocks on the surface of the Earth. The moon has been geologically dead for about 3.5 billion years, where, of course, the Earth is active to this day. All right, so that is the results from Apollo 17. Let me very briefly mention the 3 canceled Apollo missions. NASA had originally planned all the way up to Apollo 20, so there were scheduled to be an Apollo 18, 19, and 20. But in January of 1970, Apollo 20 was canceled. NASA had decided to build the first orbiting space station called Skylab, and they needed the Saturn V rocket to launch the very heavy Skylab, so Apollo 20 was canceled. And in September of 1970, they canceled Apollos 18 and 19. And you might wonder why. They canceled it due to budget cuts. They said that there just wasn't the money in the budget to carry out the mission. but I don't think that's quite true. And I don't think it's quite true because they had built the Saturn V rocket. They had built the lunar modules. They had built the command modules. They had built everything that they needed to build to carry out Apollos 18 and 19. In fact, the Saturn V rockets that were to be used for Apollo 18 and 19 are now on display at the Kennedy Space Center in Florida and the Johnson Space Flight Center in Texas. They're now museum pieces, although they were fully functioning, ready to fly Saturn V rockets. I think the reason they were canceled is that at this point, the Vietnam War was starting to attract much more attention from the American public. Protests were raging across the country about the cost of the Vietnam War. At the same time, Apollo had accomplished its mission. It had landed a man on the moon and returned him safely to Earth before the end of the decade. And politicians were quite concerned that Apollo was taking huge risks. What if an astronaut was killed in the line of duty? What if astronauts were stranded on the surface of the moon? By continuing to carry out the Apollo program, we were just taking more and more risks. It seemed to be time to move on to the next project, to close down Apollo and figure out what came next. And what came next, as we'll see in the next lecture, was the Space Shuttle program. So join me in Lecture 8 when I talk about the Space Shuttle program.